my other laptop froze. And I happened to have a second one, so I joined from the other one. Okay, right. We're going to start our UKPN seminar. Just to introduce myself, I'm Paulina. I've been part of the UK Polar Network for like a year and a half, and I'm conferences coordinator, but right now I'm putting together some seminars, and today we have Lisa Craw from Cardiff University. We met at the IGS conference and we both presented posters, and her one was really cool, and it was about the cryowurst, which is a new instrument, follows on from the cryo egg to look at the movement of surging glaciers from within. So yeah, take it away, Lisa. I'll let you introduce yourself properly, and yeah, go for it.
Awesome, thanks so much. Do let me know if you can't hear me or anything like that. I'll just share my screen. I've already showed my incompetence in screen sharing just before, so do yell at me if I've done something wrong. Already confused, already getting it wrong. All right.
Oh, amazing.
Okay. Except I can't change the slides. One moment. Here we are again. Right. Can everyone see my screen?
Yeah, that looks good.
Brilliant. So I can't actually see you. So if anything goes wrong, just yell at me and I'll stop.
We're still here. Brilliant.
Well, yeah, thanks so much, Paulina, for the invite. This is a really nice series. It's sort of a work in progress what I'm presenting, but I wanted to sort of talk about what it means to work at like the intersection of glaciology and engineering. I think it's really cool what the kind of things you can do if you accept that most things will break most of the time, which I think is a bit of a theme of this presentation. So who am I, for a start? I'm not an engineer. By background, I'm a structural geologist. So I trained as a geologist in Aotearoa, New Zealand. And I got sort of interested in what ice as a geologic material, so ice as a deforming material, when I did my PhD in Tasmania, when working on Antarctic ice cores. And now I've moved to sunny, glorious Wales to work with the Prifysgol and Hydrological Instrumentation Laboratory. So we work on making a new instrumentation for glaciology. But it's not just me. There are lots of very clever people involved in this project. I'm just the person giving the talk. So you may have heard of my PI, Mike Cryo-Jones, who's the mastermind behind cryo-egg, which is our sort of more famous subglacial probe, the famous cousin of the cryowurst. So Mike developed cryo-egg in conjunction with Liz Bagshaw, who's now at Bristol. And cryowurst was developed with Christine Dow from University of Waterloo and Brittany Main, who is also at Waterloo. And we also have lots of brilliant master's students and other postdocs who helped us out with fieldwork along the way. And the cryowurst was partly designed with 2 undergraduate engineering students. So lots of very brilliant people who know lots more about things that I don't know anything about involved in this project. So this is our setting. The glacier we're interested in is called Dunshaw. Some people will call it Donjet Glacier. Dunshaw is its original name. And it's located in the Columbia Icefield, which is the largest non-polar ice field in the world. So it's on the border between the Yukon and Alaska. And a large number of glaciers in this icefield are surge type, including Dunshaw. So surge type means that the glacier advances quite slowly most of the time for long periods of time, and then for short periods of time it will advance very rapidly. So there's those slow moving periods are called quiescent periods, and the fast moving periods are called surge periods. About 6% of glaciers in this area are surge type, which is quite a lot compared to sort of globally. So Dunshaw has quite a short periodicity, we call it a surge cycle, a periodicity. compared to most surging glaciers. So it surges about once every 10 to 12 years. We have records, historic records that go back to the 1930s, but there are observations thousands of years before that from the Kalani First Nations and Champagne-Age First Nations who live in that area. During its quiescent period, Danshore moves at about order of 100 meters per year, and then when it's surging, it's on the order of 1,000 meters per year. So it's a pretty dramatic event. So during the surge, you get really dramatic topographic changes, huge crevassing, things like that. And also a consequence of the rapid movement of the terminus is you form ice dam lakes, and those can burst and cause really dramatic flooding. So this picture on the right-hand side was taken by Luke Copeland in 2019. Those two pictures were taken just a couple of days apart. So all of that volume of water can drain really, really rapidly. And that can be a huge threat to infrastructure. There's a major highway that goes past the terminus of this glacier. And based on the mass buildup and mass accumulation in this glacier and its normal surge cycle, the net surge is likely to occur between 2022 and 2026, which is, of course, right now. So it's not surging yet, but it's in some sense overdue, to the extent that you can say it's overdue, based on the historic record that we have. So I like to split sort of the causes of a surge into two categories. Obviously, everything is sort of interconnected because it's quite a complex system, but I like to look at it this way because I like ice dynamics. But generally, these images are from this science article that I linked in the bottom. It's a really nice article. I'd recommend reading that because it's a really nice description of how surges work. But generally, I say there is an ice dynamics component and a hydrology component. So in terms of dynamics, a regular glacier accumulates mass in its upstream accumulation zone, and it advances at a rate that allows that mass to move through without any sort of major changes in movement. It tends to be in sort of steady state, whereas a surging glacier will accumulate more mass than it is distributing with its movement. So in its pre-surge state, it's accumulating large amounts of mass in that accumulation zone, and then the surge will rapidly redistribute that mass so downstream, and post-surge it's much lower than it would have been if it were in steady state. So you have this sort of cycle of mass redistribution. So that's one of the components to why glaciers surge, but it's not the only part of the puzzle, because the basal conditions are also really important, whether or not your glacier will advance rapidly. So we also need to know about the hydrology of the glacier. So these sort of so-called normal glaciers, when they're in steady state in the summer, basal hydrology tends to be quite efficiently channelized. So meltwater can drain away quite efficiently. Whereas in the build-up to a surge, we think it's likely that the basal hydrology is less channelized, less efficient. And so you end up with large pressure increases at the base, which cause the glacier to lift up, and that sort of primes the glacier to have this rapid advance. So in Danshore, as you can see, it's quite a long, skinny type glacier, and it gets a little bit narrower further down, which is interesting. So those red dots are 5 kilometers apart, and the surging in Danshore tends to mostly focus downstream, so the lower 21 kilometers of the glacier. So mass does accumulate higher up, and that seems to be a major component of its surge cycle, is that you have this mass accumulation, but we can't necessarily say that the volume of mass that's accumulated is what's causing the surge, because the surges happen on such a regular period that, of course, it's going to accumulate the same sort of amount of mass within that period. So we can't necessarily say, without knowing what the hydrology is doing, knowing what the interior dynamics are doing, whether that is actually the cause of the surge. We have really good information from satellites about surface velocities, but we do actually need to know what's happening under the surface of the glacier dynamically and hydrologically. So here we have a problem, because we want to observe what's happening under the surface of the glacier, which means we want to install instrumentation. But surges, by their nature, are very destructive. So often our instrumentation is destroyed by the actual thing that we're trying to observe, right? So if you have wired instrumentation that's connected to the surface by cables that are transferring the data, those cables will eventually break just because of ice movement. This instrument on the right-hand side, that when we installed it, this is on a Greenland glacier, not even a sedge-type glacier. When we installed that, it was on a flat surface upright. And we came back a few months later and it was on a 45-degree angle dangling over a crevasse. So these are very dynamic environments. That's why we love them. But it also means that wired instrumentation is very easily destroyed. So it's difficult to observe these types of events. The solution is wireless instrumentation. So the idea behind cryowurst and its cousin, the cryowurst, so called because it is shaped like a sausage. The idea behind them is that they use radio links to transfer data back to the surface. So the instrument itself is equipped with sensors. The sensors take measurements and they send radio waves back to the surface, and we have a logger installed on the surface which receives that information and stores it. The logger also transmits those data packets back to us via a satellite link. So there are multiple sort of contingencies in this system. If the instrument stops working, we still have information logged at the surface on the surface logger. If the surface logger falls into a crevasse and breaks, we still have all of the previous information transmitted back to us. And we can go and replace the surface logger and hopefully the instruments are still working. So enter the cryowurst. As I said, elongated, sausage-shaped. That's the only reason for the name. We just thought it was funny. The instrument itself, the casing is made of this really dense engineering plastic called POMC. It's several centimeters thick, so it can withstand quite high levels of pressure, just the instrument itself. It doesn't have a cable connecting it to anything, so just the instrument itself needs to survive and transmit. In terms of sensors, there's a pressure sensor, which if the instrument is in water at the base of the glacier, it can tell us what the water pressure is. It also has electrical conductivity. So if the water has very low conductivity, it's likely to be fresher water. If it has higher conductivity, it's likely to have been stored water or have been in the basal system for a longer period of time and accumulated more dissolved material. We also equip the instrument with a tilt sensor. So 3-axis tilt sensor, which means that when the instrument is frozen in and the ice moves or deforms internally, we can use the orientation of the instrument, the change of orientation of the instrument, to try and say what amount of shear, what amount of internal deformation is happening within the ice column. There's also a temperature sensor. The internal battery is 3.9 volts, and it should power the instrument for about 5 years. Remains to be seen because we haven't effectively had a 5-year deployment yet. But we've had them deployed for about a year and a half, and they're still very high battery voltage, so they seem to have quite good longevity. The surface receiver is installed on one of these tripods. The tripods are designed to be sort of surge resistant in that those battery feet on the 3 corners are attached by ball and socket joints to the rest of the tripod. So if the topography changes, then they should sort of self-adjust to avoid the whole thing toppling over. Again, the surface receiver is powered by batteries, 4 12-volt batteries like car batteries, and 2 solar panels. So during the summer, the solar panel should charge the instrument, and then during the winter, theoretically, those 4 batteries should power the instrument all the way through the winter. So this is our deployment. We deployed 4 instruments. I say we successfully deployed 4 instruments. We always put more than 4 in the hole and some of them break, but that's just sort of how it goes. The borehole we drilled, I should have marked on the map earlier, this location is about 1 kilometer back from the terminus, so we're quite close to the terminus. We drilled a borehole through the glacier into the base, and all of the water drained out of the hole as soon as we penetrated to the base. So we're connected to the hydrological system in some way. The 2 lower instruments have pressure sensors on them because they're more likely to be connected to the hydrological system. Also, those are the most expensive sensors. Yes, and the lower 2 sensors, we space them closer together just because we expect there to be more shear information near the bed. So, there he is. Some very silly person is drawing a face on this one. I wouldn't know anything about that. So it sounds straightforward. It definitely wasn't. So I just wanted to take you through a sort of non-exhaustive list of things that went wrong during this whole process and how we recovered from them, because it's never a straight line with these kind of projects. So in July of 2023 was the first deployment of cryowurst. Mike and Christine put 4 of them down a borehole in the location I was talking about. They were running happily, fine, no problems. Went away. Unfortunately, the instruments were consuming more power than we expected because of a fault with the power system. All of the batteries died within 10 days. Boo. Oh well, pick ourselves up, we move on. A year later, in July of 2024, Mike and I went and installed another 4 instruments in the same borehole site. Everything was going well, batteries were looking great. We got 4.5 months of data, fantastic. Unfortunately, this time the surface logger system was consuming more power than we expected. And he went to sleep in late November of 2024. So that was middle of winter last year. So the solar panels were happily powering the system during the summer, but as soon as it became dark, we didn't have enough battery power to keep the instrument running. But that's fine, right? Because the sun will come out and the entire thing will wake up again and it will keep running the next summer. Unfortunately, over the winter, an instrument that was next to our instrument was struck by lightning. Not much you can do about that. And that power surge fried our microcontroller, so our surface logger no longer worked. Oh no. So in July of this year, I went back, I installed a new surface receiver. The instruments were still working, so we are now receiving the data. We've received another few months of data. Remains to be seen what the next problem will be, but who knows? It may keep running all the way through the winter, it may not, but it will be some new exciting problem that will come up. So without further ado, here are some of the data from the instrument. I know there is a lot of information on this slide, so let's just sort of stare at it for a while. You don't need to understand all of it, but I just wanted to show off by putting all of our different data types on this one slide. I've colored the instruments by depth. So the lower one is the one that's sitting right in the hydrological system at the base. That's the green one. So the green and the orange, the one that's just above it, both have pressure sensors on them. The others don't. So just to highlight a few things, for a start, during the summer, so we're starting in July, going through to the end of November. In the summer, we have this nice oscillation in pressure at the base. So this is the daily melt cycle. As the sun comes out during the day, you get melt at the surface. That melt water percolates through the glacier system, goes into the base, increases pressure at the base, and then as the sun goes down, things cool down, that meltwater drains away. So we have this diurnal cycle in pressure, and it just sort of peaks up above the overburden pressure most days, but not all days. The electrical conductivity you'll see right when we've deployed the instruments has this huge amount of oscillation in it, and that's because the water in the borehole is just freely moving past the instruments. But once they start to freeze into the sides and become coupled to the ice, that conductivity just drops way down. So you have a very low conductivity from then on through the summer. And that's just because the water can no longer move freely up and down the borehole. But that basal instrument does have occasional peaks in it. So there is sort of some kind of stored water or higher conductivity water coming through the system, but just at the base. You notice through the summer, as we come through into autumn, the system starts to cool down. We lose that diurnal melt cycle because the hydrological system is kind of shutting down. You no longer have free water movement around the base of the glacier. But occasionally it will reactivate. So you get these sudden, quite dramatic little leaps in pressure. And that's also seen in the conductivity there. After that, through the winter, the pressure just sort of really slowly jacks up, but doesn't quite reach the overburden pressure. And it is interesting to see that when it does nearly reach the overburden pressure, even though we're getting well into winter now, it can still adjust. So we have these sudden little drops in pressure just to sort of adjust to stop the pressure from getting too high. And I think that's quite interesting. The system isn't really asleep. It's just sort of dormant. So we can see there's sort of like characteristic summer, transitional, and then winter behavior of this system. But it does divert from those characteristics sometimes when you get these sort of sudden events, which are then sort of reabsorbed back into the system. Looking at 2025 now, the behavior is actually very different from 2024, which is quite interesting. So you notice there's still this diurnal cycle sometimes in the summer, but not always. The second instrument from the bottom seems to have disconnected a little bit from the lower one. So it's just the lower one that's in that basal system now. But occasionally you get these really massive drainage events. So it's like all of the water, or a huge amount of water is just drained out of the system all at once, especially that second one. So these data points are an hour apart. So we've lost several bars of pressure within an hour, which is really dramatic. So instead of that consistent diurnal cycle, we have really dramatic events and then almost nothing happening. You also notice now we're getting into winter, things are cooling down. The pressure has actually come up above the overburden pressure and is there quite consistently, which is really different from last year's behavior. And also that basal electrical conductivity is decreasing, which is interesting because it implies that there is still some fresh water coming into the system, which is causing the overall conductivity to decrease. So summary of the hydrology, because I know that was a lot of information, but basically you could see that the hydrological system, its characteristics change from summer through to winter. It slows down quite dramatically in the winter, but it doesn't seem to be completely shut down. It can still adjust to these increases in pressure. And so far, the data from 2025 shows that the behavior hydrologically is much more erratic than last year. The basal pressure is increasing as we speak, higher than it's ever been before. So I promised you ice dynamics. What about them? I've tried to plot, orientation data is quite complicated, and I've tried to plot it in basically every way possible. So if any of these slides don't make sense, wait for the next slide. It'll be the same data in a different orientation. But basically what we're looking at here is, if you imagine the instruments were installed just initially vertical within the hole, and the hole was drilled directly straight up and down, we're recording the change in orientation of that main axis of the instrument. So as the ice deforms, as the borehole deforms, those instruments will tilt slightly, and we're recording that tilt. So obviously there's this huge data gap in the middle, but we have from the middle of summer until winter last year, and then we have from summer until now this year, still recording data as we speak. So it's interesting that the largest change in angle on these sensors happens on the second to bottom and the top. The basal instrument doesn't seem to rotate much at all. It has a very small amount of rotation, whereas the top and the second to last have the largest angle. They sort of have a slow change in angle over time, which is quite consistent. But something dramatic has happened in that data gap between late last year and summer of this year. There's been quite a large change in orientation on all instruments. So it seems like a lot of deformation happens probably in the early summer, which we've missed. This is the same information presented differently, but imagine we've got 4 instruments in the hole. We know what orientation they all are at all times. So if we just draw a straight line between them and say, this is probably the shape of the borehole now, we can sort of say what the angle of the borehole is and what the position of the base is relative to the surface based on that information. Obviously, we only have 4 points. So we only have 4 points. So it's limited what we can really say about the internal structure of the ice, but this is the best we can do. So based on this is just 2024 data. It looks like there's quite a large change in orientation of the borehole early on, and then as we get into winter, it's much less. But overall, the base of the ice sheet, the base of the borehole, has moved about 1.5 meters relative to the surface. And based on GPS at the surface, the entire thing has moved about 16 meters in the flow direction. There we go. That's the direction of flow. Now, if you remember that big jump in the data gap, jump in orientation within that data gap in the last graph, you can see that very much here, where the orange are the orientations up to the present day. So there's been a huge change in orientation of that borehole within that gap, but actually not very much change since then. That's the flow direction again. And once again, same information, but presented in a different way. If we translate the orientation of that borehole into the horizontal shear strain down the depth of the hole, so more yellow is more shear, as in more deformation within that little packet of ice. It seems like more shear strain accumulates when the basal water pressure is significantly below the overburden pressure. So if we have low pressure at the base, you get more deformation closer to the base, whereas if the pressure is higher, it's easier to have sort of block flow where the glacier just moves over the bed. If we look at the same thing for 2025, there's actually not very much strain accumulating at all. Notice that the scales are very different here because there was so much deformation in between those, in that data gap between the two data sets. But as that water pressure creeps up, there's not as much strain accumulating, and which implies that we have more block flow of the glacier. So, summary of that, we can use the orientation of the instruments to estimate the internal deformation. This is more of an art than a science in some ways, but it's the beginning of what we can do with these orientation sensors. And those sort of imply that shear is concentrated near the base when pressures are lower in the spring and summer. And when the hydraulic pressures increase, there's less need for internal deformation to accommodate that behavior. So in the bit more than a year that we've been observing it, the hydrological system seems to be becoming more pressurized and less efficient, and is accumulating less strain in the late summer. So this is the glacier in its sort of pre-surge state. So if our predictions are correct and it does surge in the next year or two, it'll be really interesting to see how those systems change and how they interact. So I just wanted to add a little epilogue to this, to say that I think the best thing I've got out of this project is the realization that anyone can be 80% of an engineer. So this is an engineering project. I'm not an engineer, but if you have patient colleagues and YouTube and you're willing to make a lot of mistakes, you can get about 80% of the way there. You need an engineering degree to get the last 20%, but almost anyone can do a lot of these things. And something we're really interested in our group is making sure that everybody in glaciology feels like they are welcome in the lab, they are welcome in the field, they are able to gain these skills. There isn't a certain type of person who is an engineer or a glaciologist. So a couple of years ago, we ran the cryowurst course, where we tried to teach early career glaciologists field skills, engineering skills, and it was really successful. We'd love to run it again. So if anyone's interested in talking about that kind of thing, please do email us. Thank you very much. I'm going to stop sharing so I can actually see you, but please do ask questions.
Thank you so much, Lisa. That was really, really nice. And it sounds like you're in a really lovely group and community of people as well. Oh, we're going to move on to questions. Luke has already asked a question in the chat. By the way, if it would be really nice to see people who are in the meeting. So if you could turn on the camera, it would be great to see your face, but also if you're not comfortable, then that's all right too. Yeah, Luke has asked, great talk. Have you considered fitting a seismometer to the cryowurst?
Great, thank you. Great question. Yes, we have, and it's a work in progress. So one of our PhD students, Sarah Mann, is actually working on this as we speak. It's complicated because of the data volume. So if you're recording huge amounts of data on the instrument, you then need to transmit that, but you're a bit limited in how much data you can transmit in what period of time. But yeah, it's a good question and something we're working on.
Mm-hmm. Yeah, I've been writing down lots of questions because you mentioned so many interesting things. Well, I'll start like towards the end. You were talking about how you're seeing all these patterns emerge in a pre-surging glacier. So are you expecting to keep the equipment in the glacier until it surges and then see the conditions that lead up to the surge completely?
Yeah, that's the idea.
Mhm.
So as I say, the glacier is expected to surge in the next couple of years. Who knows if it actually, well, I mean, it's impossible. It's like predicting an earthquake, right? You don't really know. But the batteries on the instruments should last for at least another 3 years based on their current consumption. So the idea is that we do capture the surge event, and then we can look back at what happened pre-surge and what happened during the surge.
So are these surging patterns between glaciers similar?
Yeah, good question. Not always.
Mhm.
So yeah, surges are quite complicated, and that there's a lot of different interplays between different elements, like the dynamics and the hydrology. And I think the surging is like a characteristic of a glacier that can have different causes. So yeah, we'll be saying we can examine what causes the surge in this specific instance, but I think it's just the system being out of equilibrium, and that can happen in different ways, right?
Mm-hmm. Oh, Edmund asks a question. Thanks for the question. It says, what does it cost to put one of these together?
Yeah, good question. It depends if you factor in our time or not, but thousands of pounds. Yeah, if you're interested, just email us if you want to actually purchase some. We do that kind of thing as well.
That's actually quite reasonable because it's something that you deploy for a really long time, right? If it's thousands of pounds, that's really not huge for monitoring. Yeah.
You also need the surface receiver, which is excess of £10,000, but those can be reused.
Okay. Yeah. Yeah. So if it's possible to kind of see the patterns of, well, like, can it be used as a prediction system is what I'm wondering, that if you really understand what's going on within this one glacier, would you be able to put it inside glaciers that are leading towards like areas where people are living and be able to say, oh, we think this glacier might surge, or can we already predict that?
We can't really predict it at the moment. That would definitely be like the end goal, I think, would be if we could say this is the fingerprint of the lead up to a surge, which means it's going to surge at X time. Absolutely fantastic. I don't know if we'll actually reach that point, but I think, yeah, that's sort of what we're working towards, is trying to characterize what it looks like, and so that we can predict what's going to happen.
Mm-hmm. Yeah, because it's like the pictures that you showed. To be honest, before people started talking about surging glaciers at this conference, I had no idea that surging glaciers were a thing, which
I didn't really before I started this project either.
Yeah, it's crazy. And then the pictures that you showed, there's such a big difference pre-surge and post-surge, and it seems like it's like a big natural hazard that people aren't massively aware of.
Yeah, it's a big hazard, but it's quite localized. I mean, there aren't that many surging glaciers worldwide, and they tend to be in quite remote areas. So
yeah,
and the specific glacier is of interest because it does threaten infrastructure, whereas many don't.
Mm-hmm. Mm-hmm. Oh, someone asked, great talk. Did you give the newer surface instrumentation a lightning rod, or the lightning strikes considered a very rare event?
Yeah, I would have considered it a rare event before it happened. Yeah, we didn't do anything to mitigate that in the new installation because we didn't really know how. I mean, the instrument, our surface receiver doesn't have a lot of metal on it because the metal interferes with the radio propagation. So most of it is made out of GRP, like plastic poles. The instrument that was next to it was a metal tripod. So that was what was hit by lightning, and that's no longer there. So I'm hopeful that won't happen again. But our instrument is sort of the tallest thing for miles around. So yeah, maybe it needs a bit more thought.
Okay. I'm interested in the relationship between climate change and surging glaciers because my field is climate change attribution. So is climate change going to make surges more likely? And would it be possible to use instrumentation like this for attribution in any way? I'm feeling unlikely, but the question is there.
Yeah, it's definitely related. Like climate and surging is related, mostly because I guess through mass balance. as in if you have less mass accumulation, you're actually less likely to have a surge, or your surge period should probably increase. But I don't think we really know what the relationship is. So yes is the answer, is that we should be thinking about it, I guess.
But it's still hard to tell.
Yeah, so far I think the relationship isn't that clear.
Okay, interesting. Oh, Tina is asking, great talk, Lisa. What does it mean when you mentioned hydrological system is becoming less efficient and more pressurized?
Yeah, so I sort of throw these words around and maybe don't use the very precise meaning. Basically, when you have, in the whole glacier system, when meltwater enters the system, it needs to go somewhere, right? So it generally, if it's meltwater from the surface, it will percolate through the glacier, through moulins and crevasses. It will end up at the base eventually. And if it just sits there and it's got nowhere to go, the basal pressure will just keep increasing because you're putting more and more water in, the pressure will increase. Whereas if it has somewhere to go, if there are a system of channels, like large channels that the water can flow through, that water can leave and the system is not pressurized. So if you have an efficient system, we would say that's got like large straight channels where the water can just flow away. Whereas if it's an inefficient system, maybe it's lots of little like interconnected smaller channels. It takes longer for that water to escape, and so you can accumulate more pressure at the base. Hope that makes sense.
Makes sense to me. Hopefully makes sense to Tina. Thanks for the question. Edmund says, not a question, but just wanted to say that I also really enjoyed the graphics.
Thank you.
Phil is saying, thank you for a super interesting talk. I wanted to ask, how difficult and complicated was it initially to check that the cryowursts were going to survive the conditions that they were going to be in before deploying them? I imagine that that must have been tricky to work through.
Yes, it definitely is tricky, and it's even trickier when you don't give yourself enough time to properly test everything, which is what we usually do. We benefited from cryowig coming before, so cryowig has had like proper testing in a pressure chamber and has been down under the Greenland ice sheet and all that kind of thing. So we sort of knew what worked with cryowig, but as you saw, lots of things went wrong with cryowurst that we hadn't necessarily predicted, or that we could have predicted if we had tested over a longer time period, which we didn't. So it's definitely a sort of trial and error process, but we'd like to do more lab testing. We have environmental chambers that we can test different environmental conditions and their effects on the instruments. So that is something that we try to do and calibrate everything properly.
Just out of curiosity, what testing was done on cryowurst?
So we need to calibrate all of the sensors. So we tend to sort of submerge in buckets of water with different conductivities and things like that. Cryowurst hasn't been pressure tested because we're not putting it super deep, but cryowig has been put in an actual pressure chamber, and pressure was increased to see how we deal with it and how the sensors would react. And also just leaving something on the bench and letting it run to see how the power system deals with running over a long period of time is really important.
Mm-hmm. And was it a long time from testing to deployment? And just developing the whole system?
So yeah, Mike, my PI, has been working on this for several years now. But we do need to manufacture the instruments, and there's all kinds of hold-ups and delays in the lead up to actually making the instruments. So it's never as long of a lead time as we would like before deploying them.
Mm-hmm. Edmund also asks, is there any realistic possibility of ever recovering the cryowursts?
In this kind of scenario, no, because they've just frozen in, and you'd have to, there's no way. You'd have to drill down and you'd destroy the instrument. I guess there are scenarios where they would be recoverable, but generally, if they're going deep, they're just freezing in, and so there's not really any way to get them back.
Mm-hmm. Yeah, I found some of your findings quite interesting with the ice flow profiles, because I'm an ice sheet modeler, and generally ice flow profiles are very consistent, and they're very defined by like the bed properties and just like the ice thickness. But the profiles that you showed were quite wavy. It's not like the standard of what you would assume they would be, which kind of implies that they're a lot more unpredictable than we thought. I guess my question is, how can your findings be incorporated into the wider ice sheet modeling world?
Yeah, it's a good question. I mean, I guess it's always going to be like a mountain type glacier is always going to be a bit more heterogeneous than an ice sheet. With an ice sheet, you can sort of make more sweeping assumptions, whereas when we don't really know the bed properties, the bed is quite uneven in this location. I guess the outcome would be the profile is heterogeneous, and so what does that mean? Can you test for how much heterogeneity along the profile you would need to have a certain effect on the flow? I don't know. I need an ice sheet modeler to answer that.
Yeah. Does anybody have any other questions for Lisa? Did I have any other questions for Lisa? Yeah, I had the word commercialization written down. Is that something that is thought about in your field?
Yeah, we've thought about it. I think that, yeah, we prefer to do things open source, and sort of making the instruments is difficult and annoying enough that some people will pay us to just do that. But I think the plans for the instruments and the circuit board designs and everything we make open source because it's sort of a community project.
Okay. In that case, I think if there's no other questions, we can end the session here. Thank you very much, Lisa, for coming in and giving us your talk.
Thanks, everyone.
The graphics were absolutely amazing. I loved all the little sausages and smiley faces, and it was really, really engaging.
Thank you. Thanks, everyone, for coming.
Yeah. And thank you, everybody, for coming as well. Yeah. And I'm going to stop recording here, and we can finish up.